In the vast cosmic theater of the universe, few entities captivate the imagination and challenge our understanding of the fundamental laws of physics quite like black holes. What lies at the heart of a black hole, defying our understanding of physics with its infinite density? How does the event horizon act as an elusive boundary, concealing the secrets of what transpires inside a black hole? Embark on a cosmic journey to unravel the mysteries that lie beyond light and darkness inside a black hole, exploring the enigmatic realms where gravity distorts space and time, and witness the cosmic ballet of singularity, event horizons, and the intriguing phenomenon of spaghettification. The nature of what happens inside a black hole is still a topic of intense theoretical research, as the extreme conditions within make it challenging to apply our current understandings of physics. However, based on general relativity and some quantum physics principles, scientists have proposed various theories about the interior of black holes. It's important to note that these ideas are speculative and may be refined or revised as our understanding of physics evolves. The singularity is characterized by an infinite density, meaning that the mass is concentrated within an infinitely small volume. This concept challenges our understanding of physics because our current theories, including general relativity, break down under such extreme conditions. As the singularity, the equations of general relativity produce results that become nonsensical. This breakdown signifies a limitation of our current understanding of the universe, particularly in regions of extreme gravity and curvature. The extreme gravitational field around the singularity causes a profound curvature of space and time. This warping of the fabric of the universe near the singularity is a critical aspect of general relativity. The singularity is hidden behind the event horizon, a boundary beyond which nothing, not even light, can escape. This makes direct observation or measurement of the singularity impossible from an external vantage point. Understanding the singularity requires a theory that unifies quantum mechanics with general relativity, a task that scientists have yet to fully accomplish. Theoretical physicists seek a theory of everything, or a quantum theory of gravity to describe the behavior of matter and space-time under such extreme conditions. It's important to note that the singularity is a theoretical concept based on the current state of our understanding of physics. The existence of a singularity inside a black hole suggests that our understanding of the universe may need refinement, especially when it comes to describing the behavior of matter and energy in regions of incredibly strong gravity. The event horizon is a crucial concept associated with black holes and represents a boundary in space-time beyond which nothing, not even light, can escape the gravitational pull of the black hole. The event horizon is an imaginary boundary surrounding a black hole. Once an object crosses this boundary, it is inexorably drawn into the black hole's gravitational well, and no information or signals from that object can reach an observer outside the event horizon. The escape velocity required to break free from a celestial body depends on its mass and radius. For a black hole, the escape velocity exceeds the speed of light, making it impossible for anything, including light itself, to escape its gravitational influence once inside the event horizon. The event horizon is an observational boundary beyond which we cannot directly observe anything. Even though black holes do not emit light, their presence can be inferred through their gravitational effects on nearby matter and light. One of the intriguing aspects of the event horizon is the information paradox. When matter falls into a black hole, the information about that matter appears to be lost to the external universe. This raises profound questions about the conservation of information in the context of black hole physics and remains a topic of active research and debate. The event horizon is formed during the gravitational collapse of a massive object, such as a massive star, when its core undergoes a supernova explosion, and the remaining mass collapses into a small volume, creating a singularity and the surrounding event horizon. The size of the event horizon is directly related to the mass of the black hole. Larger black holes have larger event horizons. The properties of the event horizon, including its temperature and entropy, are crucial aspects studied in the context of black hole thermodynamics. Understanding the event horizon is fundamental to comprehending the behavior and nature of black holes. While we can observe the effects of a black hole's gravitational pull on nearby matter, the event horizon itself remains a mysterious boundary, and its study is at the forefront of theoretical physics and astrophysics. Advances in our understanding of black holes, including the dynamics near the event horizon, are essential for addressing some of the most profound questions in modern physics. Spaghettification is a fascinating and somewhat whimsical term used to describe a phenomenon that occurs near the event horizon of a black hole. This gravitational effect, predicted by general relativity, results in the extreme stretching and distortion of objects that venture too close to a black hole. As an object, such as a star or even an astronaut, approaches a black hole, the gravitational forces acting on it are not uniform. The force exerted by the black hole's gravity is significantly stronger on the side of the object facing the black hole than on the side facing away. This difference in gravitational pull creates what is known as tidal forces. The tidal forces exerted by the black hole becomes more pronounced as the object gets closer. In the case of an astronaut falling feet first into a black hole, for example, the gravitational pull on their feet would be much stronger than the pull on their head. This difference in gravitational forces causes a stretching effect, similar to how tides on Earth cause the ocean to bulge towards the moon. The stretching effect due to tidal forces leads to the object being elongated into a shape resembling spaghetti, hence the term spaghettification. This process occurs gradually as the object gets closer to the black hole's event horizon. The degree of spaghettification depends on the size and mass of the black hole. Smaller black holes have stronger tidal forces near their event horizons, leading to more pronounced stretching effects. Once an object goes under spaghettification and crosses the event horizon, it is destined to fall into the singularity at the center of the black hole. The extreme gravitational forces near the singularity essentially ensure that any structure or matter that enters the event horizon is irreversibly pulled towards the central singularity. Hawking's theory is rooted in the quantum nature of the vacuum, where particle-antiparticle pairs continually pop in and out of existence. Near the event horizon of a black hole, these pairs can be separated, with one particle falling into the black hole and the other escaping into space. According to quantum field theory, particle-antiparticle pairs can spontaneously appear, even in a vacuum, as a result of quantum fluctuations. In the vicinity of a black hole, these fluctuations can lead to the creation of particle-antiparticle pairs near the event horizon. The process of Hawking radiation implies that black holes can lose mass over time. This is a significant departure from classical black hole physics, where nothing, not even light, is expected to escape a black hole. Hawking showed that black holes should have a temperature inversely proportional to their mass. Smaller black holes would be hotter and radiate more intensely than larger ones. This temperature is now known as the Hawking temperature. Hawking's theory has led to the information paradox, a long-standing puzzle in theoretical physics. According to quantum mechanics, information should not be lost, but when particles fall into a black hole, it seems that information is irretrievably lost, violating quantum principles. Resolving this paradox remains a major challenge in the field. Hawking radiation represents a crucial intersection of quantum mechanics and general relativity, providing insights into the behavior of matter and energy in the extreme gravitational environment near black holes. While its direct observation remains elusive, its theoretical implications have far-reached consequences for our understanding of the universe. As we conclude our exploration into the cosmic abyss, the singularity at the heart of a black hole, shrouded in infinite density, challenges the very foundations of our understanding. Delve deeper into the mysteries of the universe by subscribing and staying tuned for more celestial revelations on our cosmic journey.